In Unit 1, Module 3's Check Your Understanding, we're working through several problems that are building off of your knowledge of what is a periodic function. So in the first few problems, we're just being asked, what is it a periodic function that we're looking at? And if so, what's the period? And if not, how do we know? So to do these, the key is going to be what is a periodic function. And so when thinking about that, you really are looking for a function that repeats sort of on a cycle. So it's going to return to an original point and then follow the same pattern again and again and again. So when telling if a function is periodic or not, I often like to look at high points. And if you notice here on the graph in number 1, we have this high point here, but we never reach that point again. In fact, the function seems to be getting smaller and smaller each time, or sort of closer and closer to 0. And so we actually don't have a repetition here. So we would say this is not a periodic function. And it's simply because the points don't repeat. So there's no repetition. We don't see that high point coming back a second time. We don't see this low point coming back again later in the graph either. You could compare that with the graph in number 2. If you notice here when x is -5, we have this high point here, and we come back to that very same high point over here at 2. And so we'll notice that it repeats, and it sort of follows the same, slightly down, steep up, again in the next pattern. And we can even check here with our low points. So we have a low point and a low point. And so yes, this is a periodic function. And even if you weren't certain from just sort of its seeming, you could double check that these two high points are the same distance away as these two low points. And so here we would count 1, 2, 3, 4, 5, 6, 7. And down here, the low points are 1, 2, 3, 4, 5, 6, 7. And so our high points are 7 away, our low points are 7 away. And guess what? That would be our period. That's how often the function repeats back to the sort of original pattern and repeats again. When we're looking at tables, it's actually sort of similar. You want to look for those repetitions. And again, I recommend looking at maxes or mins. So here I notice my lowest point is -5, and it comes back to -5 down here at 15. And if I sort of notice in between, the next 3 numbers would be -1, 2, 6. And if you notice after this -5, I have the same 3 numbers, -1, 2, 6. So yes, this is a periodic function. And the period would be the distance between getting from that -5 back to the -5 again, which was 15 units. So it's one thing once we know a function is a periodic function, there are certain characteristics that we sort of use to describe those periodic functions. And that's what questions 4 and 5 are looking at 4, 5, and actually 6. I'm going to walk through some of these and then give you answers to the other ones, but maybe not focus on all the parts, because once you sort of do this once, you'll notice that the values are sort of similar. So this graph's pretty straightforward. Again, you might want to look at high points to answer some of these questions, or low points. Those are helpful values, especially when dealing with the period. So I'll notice this period goes from -10 all the way to -1, so that would be a distance of 9. Now, when doing the midline and amplitude, I actually like to build off the min and max. So our max value is going to be the highest y value, which in this case is 2, and our minimum is going to be the lowest y value, which in this case would be -8. Well, if I'm looking at the distance between these two, there's 10 units. Well, a midline should occur exactly halfway between those 10 units. So that would be 5 units below that high point. 1, 2, 3, 4, 5. That midline becomes sort of the middle value from which our function rises above and below. And we typically write it as a y equals equation. So y equals, in this case, -3. And then the amplitude is that sort of distance between the the sort of distance between that midline and the highest point, or the midline and the lowest point. Sort of how much does it fluctuate from that midline, in which case in this problem it was 5. And both of those numbers become important when we go and we start actually writing equations for our periodic functions. The next two problems is a little bit of function notation review. Here we're asked if we had an input of 17, what would our output value be? And so in this case, you'll notice 17 isn't on the graph. But we sort of can use our period to figure this out, because 9 before 17, so I think sort of 17 minus 9, that would be one period before, we're at 8, and if I subtracted 9 again, we would be at -1. And so what was the y value at -1? Because every time we have a period, we're back to the point that we began at. And so in this case, at -1, the y value was 2. So it's looking for that sort of repetition. Similarly, here we're asked, okay, we want different x values when our output is -3. Now in this particular case, you might notice, oops, I don't want to use red because the graph is red, so let's use orange. If I go to -3 here, that's sort of our midline. And so I want to sort of figure out, where does my graph hit the midline? And in this particular case, it's not an exact value. I'm sort of erasing so you can see a little clearer. It's a little past 1 here. So I might call that, 1.25. So I know one of the x values would be at 1.25. Now that particular x value would be on the graph. So I wanted x values that are not shown on the graph. So I would want to think 9 past that. So, if I add 9 to this, I would get the next x value that has an output at -3. And so 9 plus 1.25 would actually be 10.25. And I could keep repeating this pattern. That's how periodic functions work. So if I went 9 past that, I would be at 19.25. And if I added another 9, I would get to 28.25. And you could keep going and going and keep adding 9s, or you could subtract 9s to work sort of backwards, and that would sort of figure out where these values, equivalent values would be. There are an endless amount of possibilities of places where this graph would be equal, the output would be equal to -3. These are just some possibilities. So you'll notice on questions 5 and 6, you're basically being asked to do similar things that we were asked on question 4. The difference here is you'll notice that on graph 5, we have some vertical asymptotes going on where our function doesn't exist. So it looks a little weirder, but we can still sort of see a repetition of the pattern. And for me, I actually looked for sort of this shape in the graph. You'll sort of notice this sort of bend right here at 0. And that exact same shape is repeated here at pi. And I'll notice, I have a vertical asymptote, then following that, it sort of comes down and sort of crosses and bounces. And that same pattern then is shown, after the graph. And so I would say there is one period of my function, which was pi. And so knowing that every pi my graph repeats and I come back to that point at 0, just so you know then, if I'm 3 pi out, we're going to just be back at that 0 point. So it's a similar sort of strategy. Knowing this period of pi, we can look for that repetition in the functions. Just like we did on number 4 there, if we know that this particular point at 1.39 has the output of -0.798, we can find all of the other x values that have that sort of output by taking 1.39 and basically either adding pi to it or subtracting pi from it, and we would find the subsequent output values. When looking at a table, you're going to treat it just like a graph. If you're nervous, you could sketch yourself a graph. But, again, it's really just looking for those repetitions, just like we did on determining whether or not it was a periodic function. You can go low point to low point or high point to high point. You'll notice this one, we have a distance of 12. your midline's going to occur halfway between that. So in this case, that's going to be, halfway between the high point and the low point. And in this case, the low point's at -5, the high point's at 6. So yes, it is possible to have a midline that's at a fraction, because between 6 and -5, we got a distance of 11, which makes our amplitude 5.5 and puts our midline at actually 0.5. So we're at a sort of fraction here, and that's okay. There's nothing wrong. Midlines can occur, at all sorts of places. Just sort of depending on the function. The only one that might look a little different here, you'll notice, we're asked about when the input is -10 and then we wanted to add 3, we're sort of shifting it up 3. So in this case, think about that period of 12. If I added 12 to that 10, I would be at f of 2. So f of -10 is going to be equal to the value at f of 2, which in this case was -1. -1 plus 3 equals 2. So notice how I'm sort of using a little bit of that. I'm using that period again to help me sort of figure out where these subsequent points are going to be. Similar with the 30, if I subtracted 12 from that, I work my way backwards, that would put me at f of 18, which is on that table at 6. All the places where we're equal to -5, they should just be 12 away from each other. So the last one on the table is at 12. So 12 more from that would be at x equals 24, 36, 48, or we could work backwards and -12, -24, etc., etc., etc. Hopefully you sort of have a sense of identifying some key characteristics of our periodic functions.